last one, so hopefully you didn't miss me too much. I'm sure you didn't. I heard Jim Green gave a great talk, and I watched a little bit of it. I was in a different continent, but I managed to see some of it through the wonders of the web. So this is the last lecture of this semester. We have some plans afoot, which I think will be kind of fun for next semester, but I won't spoil anything yet. We are hoping to get Thomas O'Buchan back. If you remember, he was our scheduled speaker for October. The Vice President decided he needed him more than we needed him and took him to Denver with him, and so he had to cancel on us, but he did promise he would come back. Right now we have him scheduled for January 25th, but that may change. He's an important person, and his schedule is dictated by other people. So, but Thomas will be back at some point in the semester, hopefully in January. Anybody know what today is? My accent is a hint. It's St Andrew's Day. We used to get a school holiday for that, but not anymore. So, patron saint of Scotland, November 30th. So, the beer was on me, which hopefully you took advantage of it. Anyway, this year has been a really interesting year from the perspective of space anniversaries, Sputnik anniversary and Apollo 17 anniversary. There was another one. And I'm going to boast to everybody here, because most of this audience will know who this person is. Everybody know who Valentina Tereshkova is?
First Soviet astronaut woman.
I actually got to meet her. That's why I wasn't here the last time, so I got to meet Valentina, which was just absolute. First woman ever to be in space. She went into space even before I was born, but she still could probably kick my butt from here to next week. Really interesting person. So that was a real thrill for me. So that's my boasting over. So a lot of anniversaries this year, and one of the ones that is kind of exciting for me was Voyager, because when I was a brand new teenager, Voyager was sending pictures back from some of the most exotic places in the solar system. And so I've kind of, as an astronomer, I've kind of grown up with this notion that Voyager was the kind of thing that got me started. And so this year, as you know, is the 40th anniversary of the launch of the Voyager spacecraft, and we're fortunate living where we do to have some really good people nearby who are heavily involved with the instrument. So that allows me to segue into my introduction. Tonight's speaker describes himself as a space groupie, and he has been, I think most of you will resonate with that, he has been since the Gemini days in the mid-60s, but he actually got his first formal introduction to the planetary sciences, which has been his work since then, when he was a NASA planetary geology summer intern at JPL. And this was during the Voyager 2 encounter, I presume with Jupiter, the Jupiter encounter. And because of that experience as an intern, he's been very active in promoting internships in the sciences and in the space in general. So he's an advisor for the Lunar Planetary Institute Summer Intern Program. Undergraduates who are out there who are interested, you can talk to him later. Paul has his PhD from Washington University in St. Louis under Bill McKinnon. He arrived at LPI in 1991, and he's been working on Voyager, Galileo, Cassini, with the imaging systems on there, basically to map the topography and the geology of these icy outer planets. He says he's dabbled a little bit of it in the Moon and Mars, which is an increasingly interesting topic these days too. He's the author of the Atlas of the Galilean Satellites, and he's also, since in the last few years, he's a scientist on the Dawn mission, which visited an asteroid, on Cassini, which we've heard a lot about. It was another anniversary for Cassini this year, or the demise of Cassini was this year. And he's been studying the impact cratering of small bodies and plume deposition processes on Enceladus. And so there's a lot of this outer solar system stuff. This is your man. And so please join me in welcoming tonight's speaker, Paul Schenk.
Did he mention New Horizons and Pluto? I don't remember.
Say that again?
Did you mention New Horizons and Pluto?
Oh, and Paul's going to mention New Horizons and Pluto. Right?
So
think of the outer solar system and all these missions, and think of Paul.
Boy, humans really do like anniversaries, don't they?
It's one of those years.
So I have to ask, how many of you were here on this planet in 1989? How many of you are old enough to remember Voyager? Most of you. Good. Okay, very good. So as the slide says, that decade, or that 12-year period, was actually turned out to be pretty important in human history, or at least human knowledge and awareness of their surroundings, the solar system in this case. But perhaps Voyager did something a little bit more than that. Now, this is going to be sort of a retrospective and sort of a personal perspective. And there'll be some science thrown in, and there's no equations, I promise you. But let's start off with the story. And the story starts out in 1966, although actually technically the story starts with Galileo in 1610 when the Galilean satellites were discovered. Although technically Jupiter itself and Saturn were known to the ancients. But in any case, as planetary systems, these were discovered in 1610 by Galileo. The exploration of those systems began in earnest in around 1966 when a young graduate student at Caltech was asked to formulate trajectories to the outer solar system. And that time we hadn't even landed on the moon yet. And we had just soft landed on the moon with automated spacecraft. And he found that if you waited just long enough, at a time period in the early 1980s, all four of the giant planets, Jupiter out through Neptune, and also Pluto as it turned out, will all be on one side of the sun. And this alignment, because of the rotation periods of the four planets, only happens once every 173 years, so you have to go back to Thomas Jefferson to see the previous one. And it was one of those things that was just uniquely timed that we had the capability, or with a little bit of additional development, to do it, and that capability be ready just in time. But as the way NASA usually works is the grand idea is put forward, and the powers that be say, oh, this is too expensive. And they say, no, you can't do that. Come back to us with a smaller idea. And you have to ask yourself how much is too expensive. This idea was to send 4 highly automated, self-reliant probes that would require a lot of development to the 4 planets, the 4 giant planets, and Pluto. And New Horizons comes into this later on 2 trajectories, and you see those trajectories up here. And those trajectories, of course, were not flown exactly, but they're flown actually pretty closely, with the exception of Pluto. In 1972, NASA approved a much more reduced concept, which was to send 2 pretty advanced, although not as advanced as the Grand Tour idea, 2 spacecraft on 2 separate trajectories to the 4 giant planets. And it was called Mariner, Jupiter, Saturn in those days because the planetary probes were called the Mariner program. And what happened was that Jupiter and Saturn were authorized. You could go there. And only if the mission was successful, and there were some technical problems on the way, which we can talk about later, only if you were successful there could one of them go to Uranus and Neptune. And as it turned out, we got there, but it was kind of shaky at times. And you see a newspaper clipping. This is from my groupie days. I collected newspaper clippings of all the space missions of those days, and that's one of those. And that was in the days when they had newspapers, and that was something that occurred on a sheet of wood pulp with lettering on it. It was delivered to your home. I mean, this is a weird time, I'm telling you. I don't even know if they delivered newspapers to homes anymore, but anyway. Before Voyager got there, actually, there was something called Pioneer 10 and 11. Pioneer 10 and 11 were sent ahead launched in 1972 and 73 to scout out the outer solar system and find out whether it was safe. No spacecraft had ever been past Mars as of 1972. So there was, is it going to get crushed by the asteroids, or the radiation belts around Jupiter destroy it? And we didn't know, of course. And we now know, of course, the asteroid belt is very sparsely populated, and the chances of hitting anything are like 0.00001, or even less than that. But in any case, what we didn't know, Pioneer was an interesting little spacecraft, plucky, courageous, and all that sort of thing. But it didn't have a lot of high-powered instruments. This was done very cheaply. I don't even remember what the budget was in those days. And this is an example of one of the photographs that Pioneer returned. Glorious and wonderful, but not a lot of detail. And those of you who have followed Juno, which is the orbiter around Jupiter right now, you see some of these spectacular images that they've returned of the swirling cloud decks and thunderstorm heads and all sorts of fun things that they're seeing. Well, Pioneer scouted out was primarily to scout out the radiation belts, is what it was really designed to do. So it didn't really get very much in terms of the planet so much, but it did see a few things, and these were the best views of the 4 Galilean satellites, the 4 that were discovered by Galileo. They're all planet-sized or moon-sized, so they're substantial objects, but Pioneer didn't have a high-powered camera on board, so it couldn't really tell us very much about what was going on those bodies. Now, launch. In the meantime, Voyager was constructed and built and then put on the launch pad. So there were 2 spacecraft that were launched in the summer of 1977, hence the 40th anniversary, which is what we're celebrating today, or this year, sorry. But it's useful, I think, to think back about what we perceived about the solar system in those days. And again, I forgot to bring it, but I've got this classic book from 1960 called All About the Planets. It was for children, grade school people, and grade school kids, that sort of thing. And it was line drawings and that sort of stuff. And it had like 1 paragraph on Galilean satellites and like 2 pages on Jupiter. And it's like, it's very cryptic comments. And it's like, the solar system in those days was a very sedate, stately place. All the planets went around in their orbits, nothing changed. Maybe a stray comet came through. That was about it. Nothing much dramatic happened out there. And this, which I think is from the Hale telescope, I think, in California, I believe, shows there's cloud decks on Jupiter and all that. Even more interesting is the concept. This is an actual Voyager press release, if you will, to sort of whet the public's interest in terms of seeing, well, what kind of things are we going to see at Jupiter? And this shows the concepts of, best concepts of what those satellites look like and how they compared in size to the moon and other bodies and stuff like that. And you can see, like Ganymede, which is the top middle section, showing us these triangular icebergs floating around in a giant global sea. And actually it was kind of prescient in a certain sort of way, but it's not really accurate. Ganymede looked very much different, and of course Europa and the other ones are all out there. So March 1979 got there, and one of the things that Voyager had, of course, was a camera, a telescopic camera. And it returned all sorts of exquisite photographs. And because it was going through on a trajectory that was a one-way trajectory through the solar system, basically it looked like a boomerang going through, in and out, on a I guess it was a hyperbolic trajectory. It had 1 shot through the Jupiter system, but as it approached, it could take continuous photography of Jupiter. And you can see this is an example. I have another example later on, which is even more dramatic than this. This movie was actually reconstructed in the past 5 years or so by what we call amateur scientists. There's a group of people out there who are really kind of like the current space groupies. And they will go through the archives of the raw images and reassemble them, because people like me, we don't have time to do that. There are thousands of photographs that actually go into making these movies. And they will go and do that, and they'll just plow through them and reassemble them and do the proper color stretches. And that's, somebody has actually done that. It's a really spectacular job that they've done. And they do this all the time. It's just, I'm glad somebody has the time to do that. The big thing, though, was, of course, that Voyager, remember those images I showed in the previous slide of the cryptic crayon drawings of the Galilean satellites? This is an example on the right of what Voyager saw with a color tone applied to it. And you see this big umbrella sticking out of the side of the limb, and that's an actual erupting volcano on Io. The three outer Galilean satellites are all ice covered. Io is not. It's dry. It's got some sort of silicates on it, and it's also got sulfur on it. But it found active volcanoes. The first place anywhere other than Earth that we had seen that. We've seen volcanoes on Mars, even a couple on the Moon, but they're dead. Nothing's happening. Just, it's long since gone into what's the word? Extinct. The volcanoes are extinct. But on Io, there were about 20 active volcanoes, all venting huge amounts of sulfur and sulfur dioxide into space. That was revolutionary. And we also saw tectonics on Ganymede and other things which were quite interesting we did not expect to see. Enter July 1979, about 4 months later, Voyager 2, the second spacecraft, passed through Jupiter. And around the time of Voyager 1, which was in March, I got a letter. I'd applied to a NASA internship program, and I got the letter, and I still have that letter today. It's nice and pristine. It hasn't been crinkled or anything like that. It's like came out of a vault almost. It's probably my most prized possession, actually. And there you see on the upper left is me, and the person in front of me, who's looking quizzically to the side, is Dr. Ed Stone, who is the project scientist, one of the smartest people on the planet. And he was in charge of 11, I said 12 earlier today, but it's actually 11 prima donnas and their instruments, keeping them from killing each other, trying to get time to observe the planets. And they all did a really good job. They were dedicated to the task. But he had to keep them all in line and make sure that everybody had a fair share, and he did a great job on that. But that's me as a lowly intern standing behind him in the daily briefing that we had every morning to go over the results of the previous downloads of data on the previous day. That was part of the routine back then. And several of the people in the foreground are actual team leaders for the various instruments. And of course, in those days we didn't have cell phones, so I only have one selfie from the time period, and it was actually taken by somebody else. And the color is horribly faded. It's on an organic material called a print. The color is going bad, but I managed to restore it, so it's kind of cool. So I found that actually last week. It had been lost for a couple months. But anyway, so you might ask, what did I do as an intern? Did I do science? Did I discover great other volcanoes? No. I was immediately introduced to the copy machine. I had arrived at JPL in Pasadena about 2 weeks before the Jupiter encounter. As you can imagine, we're taking pictures as we go in, we're getting a lot of data. Everybody's excited. Every day is getting better and better and better. So you arrive in a beehive, and you're immediately put to work. Once that had subsided and we'd passed Jupiter, which was around July 9th, I think, things started to quiet down, and I could be put onto my task. My task was actually to put together, what's the word for this? Planning maps for the Saturn satellites. We hadn't been to Saturn yet, so we had another year and a half to get there. They wanted to make sure that the planned sequences that they had, we're going to take a picture then, we're going to take another picture, so many hours after that, whole sequence. They wanted to get complete maps of the entire surfaces of all the major Saturnian satellites, and there's about 6 of them. So in order to test those sequences and make sure they had coverage, they had me design these maps that showed where the mapping coverage was going to be on a particular side of the planet, or moon, sorry. And I had to draw, get access to the high-powered graphing paper and rulers and protractors of the day. We didn't need, actually, to use any high-powered computers. This was more than sufficient to see what we needed to see. So what you see is basically those polygonal outlines are where the mapping coverage was at that particular time, and you can see that it's partial coverage, it's okay, and then the one on the right is an actual complete observation of at one particular time. So it's quite amusing to actually see these diagrams, and then I can compare them to actual Voyager maps that were made. And they did a good job, and everything's all worked out perfectly fine. It was an interesting introduction. But graphing paper and ruler and protractor are still useful, just something for your teachers to remember. The other interesting aspect of being there was that there were television monitors, and this is old style tube televisions, if you remember those, not solid state like they have today. They're about the size of this thing and about that deep as well because of the electron tubes. And they were scattered throughout the lab. I mean, the Jet Propulsion Laboratory is about as big as the Rice campus, maybe a little bit bigger than that. And they're like a couple dozen buildings. Each one of them had these monitors scattered all over the lab. And the project showed each image across the entire lab as it was downloaded from deep space. So everyone got a chance to see the image. And each day you could see Jupiter getting a little bit bigger and a little bit bigger and a little bit bigger. And the detail, of course, would get more exquisite. And you could actually just ride along with the Voyager, as it were, during the course of the summer. Something I'll never forget. Now, when you get to the moons, you don't see the detail until the last day because the resolving power isn't there. You need to actually get really up close before you can see the fractures and the craters and all that sort of stuff like that. And Voyager 1, because of its trajectory, did not see Europa, which is the second moon out. And if you know anything about space science, you know that Europa is pretty important. And I'll get to that in a bit. So Voyager 2, the big surprise was Europa. What was Europa going to show us? The distant images were very fuzzy, showed only a few faint dark markings, looked like one of Percival Lowell's maps of Mars. And then that image showed up on our monitor on the right, and our jaws sort of dropped open, and it's like, what the hell is this? As this looks like no other surface we've seen in the solar system. Even since then, any other bodies that we've seen just don't look like this. It looks like a Jackson Pollock painting is what it looks like to me. So we'll see this again later on, but that tells you something about the experience of being there, because I remember there were like a half a dozen of us in a small meeting. We were waiting. We knew when the downlink was going to happen because it's scheduled out, because you have to allocate the DSN time and all that sort of stuff. So we knew when this was going to come down. We were sort of waiting. It's like, what is that? So then, the summer goes on.
Sunlight penetrated. Black light brilliantly illuminated the splendor of the rings, like the spokes of a gigantic Catherine wheel.
Anyway, we'll just let that play.
Sunlight penetrated. Black light brilliantly illuminated the splendor of the rings, like the spokes of a gigantic Catherine wheel.
Okay, so what you're seeing is we're moving forward now in the Voyager sequence, because we've only got an hour here, to Saturn, which was in November 1980. I'm sorry about that. I forgot that I borrowed this clip from something I downloaded from the internet. You could do the same thing at Saturn as you did at Jupiter. You can take movies on the way in. And of course at Saturn, the big thing is the rings. And people were blown away. They didn't really have a sense before we got there that the rings would be so complicated. You could see in the still version that it looks like a phonograph record. How many people remember what a phonograph record is? It's a sheet of vinyl about this wide, and it's got these lines all grooved in it which record the music in an analog format. It's like, okay, well, never mind. You can sort of see that on a CD-ROM, I guess. But in any case, thousands of spiral lines. It looked just like that. It's so dense in its pattern. But then, as you saw in the movie, there are these dark markings, broad dark markings that sort of swept around. It looks like somebody had drawn in crayon on the surface of the rings. People were just blown away at the complexity. And the rings, of course, are an experiment in gravitational physics, because there are like those half dozen moons that I described. They're out beyond the ring system, but there's also about an equal number of half dozen or so smaller moons, which are about in the 10 to 100 kilometer size range, that orbit very close to the outer edge of the rings. Now, all these moons buzzing around on the outside have serious gravitational perturbations on the individual ring particles, and they disturb them in wave-like patterns, and you can see those And the Cassini mission that David mentioned did a much better job on all this and was able to document all these gravitational interactions in much greater detail than Voyager did. But Voyager revealed them. That was the key. Voyager said that there was something worth seeing out there. And it was wonderful. Now, on the other body, you have smog-covered Titan. I'm not going to talk too much about this, although it's a pretty important body in its own. It's larger than the moon. It's about the size of the planet Mercury or so. Yet Voyager saw nothing. It saw just a tennis ball, fuzzy orange tennis ball. Why? Because it's covered in smog. How many people have ever been to LA? LA has actually gotten a lot better, but actually in the late 70s, early 80s, it was still routine to see or not see the San Gabriel Mountains, which hover over the JPL site because of the smog. It's a lot better now. Usually I rarely see that now whenever I visit. But in those days it was still a problem. But Titan is just covered in it. You can't see it at optical wavelengths. At infrared wavelengths you can actually see through the smog. And of course radar will pass right through it. So Cassini carried a radar instrument, and I probably should have had some slides in here showing some of the exotic terrains, but I wanted to focus on Voyager. And they see lakes, and they see streams, and they see all sorts of things on Titan which indicate precipitation is going on, or has been, except in this case it's not water, it's a methane cycle. So methane gets converted to ethane, and the ethane precipitates, and it creates channels. Intermittent, it's kind of like dry valleys in the deserts of California. You get occasional thunderstorms once or twice this summer, and then the rest of the time it's dry. So it's kind of like that. But in terms of organic chemistry, Titan is one of the key places. Voyager got our first window into that because it had an infrared detector that was actually able to measure the abundances of these organic compounds for the first time in a reliable way. And it told us, again, Titan is a key place we need to go to, and after that, the impetus was to design Cassini and go. So, we have two more bodies that are of interest to us on the Voyager story, and the second is Uranus. And January 1986 was important for more than one reason. Those of you who are old enough will remember that reason. 4 days after the encounter was when Challenger was destroyed. I do remember that because I couldn't go to the encounter, and I turned on the TV to see what the latest Uranus results were from the press conference the day before, and I woke up to Challenger. So those of us who were around remember that very well. But Uranus was a surprise in many levels. One was that Uranus was almost as bland as Titan was. We couldn't see any storms. Part of that was because Voyager didn't have any infrared filters in the camera. Also, it's because it's kind of hazy, and it was also southern summer. The sun was almost directly over the southern pole. Hubble Space Telescope has seen clouds since then, so we do know they exist. But the big surprise was, first of all, we knew that there were rings, and so we got some good ring images. They're very much thinner, almost like 9 individual strands. There's also some dust in the system, but it's nothing like the complexity of the Saturn system. It's still an important variation on the ring theme, but the biggest surprise at Uranus was the complexity of the icy moons. Again, it was kind of surprising we were surprised because at Jupiter and Saturn we saw interesting icy moons, that they were complex and geological, so we shouldn't have been surprised, and yet we were. So it's kind of, we were still learning the lesson, as it were. So those are the 5 large moons of Uranus, and to give you a sense of scale, the largest one is about the size of Texas. So we're not talking moon size here, we're talking somewhat smaller. So to have this kind of activity, geologic complexity on something that should be frozen solid and quiet, is part of the big puzzle that Voyager unlocked for us. So there's that. See, same thing happened here. It's because I have the sound on for my last set of slides. Yeah, it doesn't give me any
These
control.
large spots are in fact huge hurricane-like storm systems.
Okay, so what you've seen here is a set of, again, time-lapse movies that Voyager took on its approach to Neptune. You can see some of the swirling cloud motions that are different, again, than what we saw at Jupiter and Saturn. You don't have these turbulent eddies and stuff like that. You have this large dark spot which sort of moves around like a giant slug almost, and then these bright streaks of white, bright high clouds. Again, a different planetary environment that we're seeing at Neptune. And in this case, Neptune and Uranus are different from the larger Saturn and Jupiter in that they have more methane and ammonia in their clouds, which give them the blue color. But they're so far from the sun that they don't get a lot of sunlight. So what's going on here is that the turbulence is different, the atmospheric patterns are different. I'm not an atmospheric scientist, so I'm not going to try to explain it. But you saw some of that here. This was in August 1989, and at that point I was actually working at JPL as a postdoctoral scientist. And all of our friends and my colleagues were all gathered at JPL to witness the encounter, and it was like a reunion. It was a very special time. There was a lot of nostalgia there. There was a lot of, probably a few tears, I think, because I knew that this was sort of the end for Voyager. It wasn't really the end, but it was the end of the prime mission. It was the end of the 4 planets that we were targeted to encounter. It's interesting to note that shortly after this, within a few months, several of our colleagues had gathered and started planning how are we going to get to Pluto? How are we going to finish the Voyager mission? And it took a full decade for that mission to actually get approved by NASA and get selected. But it started right after Voyager 2 at Neptune. Now, the other fun thing about Neptune is that Neptune has a large moon. It's called Triton. It's ice covered, just like the other satellites, except this one's different. It's got frozen nitrogen on its surface, it's got frozen methane, it's got frozen carbon dioxide. All these, of course, are gases here on Earth, but the surface temperature of Triton is about 35 Kelvin, so all these gases freeze out onto the surface and form part of the bedrock. And this is a map that we made at the LPI based on the latest map. My work in this case, reassembling the Voyager collection to make a new map. And basically what this video is, it's a simulation of the Voyager encounter. Voyager passed like right over, within 3,000 kilometers of the North Pole of Neptune, and it did a dive like this and passed by Triton on its way out. So Triton was the last solid piece of the solar system that Voyager saw. And when they presented these results to the public, the quote was, "What a way to leave the solar system," and I can agree with that. So it was pretty cool. And some of you may remember that, and this was one of Carl Sagan's projects, was that Voyager had a unique perspective at that point. I believe this was Voyager 1, which is up above the plane of the solar system, long past Saturn, was that this is the first time we had a real camera out at the edge of the solar system. Why not take a picture of the solar system? Well, that's not so easy. To do that would have required several hundred pictures to do a complete XYZ mosaic. So what they did in order to get pictures down and take them was to photograph them in this pattern, knowing where the planets were at the time, and leave the rest of it blank, because you're just going to see nothing. It didn't have the sensitivity to see anything more than the brightest stars anyway. And you can see the small little boxes show the insets, and this is the origin of the pale blue dot reference to the Earth, because in these images the Earth appeared blue, commonly because of the water, obviously. But it was just a dot, 1 or 2 pixels wide. It was not very large at all, of course, at that distance. So it was a very famous photograph. It was the last set of photographs that Voyager took. The mission was not over. This diagram shows the approximate current positions of the two Voyagers and the two Pioneers. They're all headed out to the deep space. We've lost contact with both Pioneers, mainly because the power ran out. The isotope generators were of limited capability, so the power ran out after 20 years, or maybe it was about 20 years actually, that they ran out, didn't have enough power to run the antenna. But Voyagers are still running strong, and this diagram is probably a little out of date because Voyager, it's either 1 or 2, I don't remember which, have actually passed the orange boundary and are now into the beginnings of what we would call intergalactic space in terms of particle physics and that sort of thing, the edge of the solar influence. The Voyager mission ends sometime in the next decade when the power basically runs out and can't run the transmitters. Basically, it's running only a few instruments at any given time to measure the particle and radiation fields. And in about 40,000 years, if you set your watches, you can note the passage of Voyager 1 as it passes these reference stars. Those of you who are astronomers may recognize some of these names, Ross 248 I think in particular. And I think in about 100, maybe it's 200,000 years, I think Voyager 2 passes within a light year or so of Sirius. And those of you who are astronomers will recognize Sirius as the dog star, the brightest star in the sky. So it actually will not pass too far from it. Whether anybody will notice, I don't know. So having told you the Voyager story, we can quickly take a look at what we've learned from Voyager. Again, this is the slide I showed earlier. It's the telescopic pre-Voyager photograph of Jupiter. And this is one of the Voyager images, movies of Jupiter. And it's worth playing again. Okay, it repeats. Watch the southern edge of the great red spot, how it sort of eats and then burps out these blobs of clouds as it rotates. And the upper cloud decks, as they swirl around at different rates, shearing past each other. There's so much dynamics going on here. It take decades, and it has taken decades to figure out what's going on. In fact, they had to launch a new mission to actually figure out why these patterns look the way they do. These are representative images of the 4 giant planets that Voyager visited. And again, they learned so much about the magnetic fields. You have to go there to actually measure the magnetic field. And I've got a slide later on that shows it, but the magnetic fields of both Neptune and Uranus are tilted like about 45 to 90 degrees from the rotational axis. So the rotational field is actually doing this as the planet rotates. Ours is pretty close to the axis of rotation. So nobody really understands why they do that, except probably that the magnetic field is generated closer to the surface than it is on the Earth. The magnetic field of Earth is generated in the core, really close to the center. And then, of course, the ring systems on all 4 of the bodies have ring systems. Voyager discovered the ring system of Jupiter. The Uranian and Saturnian ones were known before then. It was suspected at Neptune, but Voyager confirmed that, in fact, there is a complex ring system there. Again, this is the pre-Voyager view of the icy satellites. And this is what Voyager saw. And just the thing I want you to take away from this is the incredible complexity and diversity of these bodies. They're all mostly dominated by water ice with an admixture of some other ices depending on their position relative to the planet and to the sun. The ones further out have a lot more of the exotic ices, the methanes and the nitrogens and the carbon dioxides, whereas the inner ones are more dominated by water ice. But they're incredibly complicated. And Voyager hinted at something that was actually pretty important. And it turned out to be much more important when we returned to those systems. Europa, which is the image that's on the left-hand side, has this, again, this Jackson Pollock-like textures on it. And we suspected, but Voyager didn't have the instrumentation. It didn't get close enough to really tell us, is there an ocean underneath the surface of this ice shell? It's 100 degrees Kelvin, which is about minus 170 degrees Fahrenheit, something like that. And so it's very frozen on the surface, but it's warm enough theoretically, to be liquid underneath, which means there would be liquid water, a vast body of liquid water underneath the frozen ice shell. Voyager couldn't confirm it, but when we went back with the Galileo orbiter orbiting around Jupiter, it could pass within 50 to 100 kilometers of Europa and the other satellites as well, including Ganymede, and measure the magnetic field distortions. And that was key. Getting that close with the new spacecraft, you could actually measure the distortion and determine that it was generated from inside Europa and inside Ganymede and not Jupiter, which meant that there's something generating those magnetic distortions. And the only thing that can conduct in that way is liquid water. Also, the fact that the surface is almost crater-free. The surface is probably less than 100 million years old. Voyager determined that pretty reliably. So that was our first clue, that something that's only 100 million years old. The Earth is about 4.5 billion years old. So is Mars and the rest of the planets. But that kind of young surface has to be continually renewed by something. So there's a lot of activity, a lot of heat inside Europa.
What are the patterns that are for, I mean, what forms those patterns outside?
Fractures. When you look up close at Europa, it's just densely covered with fractures that crisscross like a ball of twine almost, is what it looks like, but it's actually cracks in the surface that are split. In some cases, liquids coming up from below and creating deposits, so that's what creates the orange material, for example. But when you get up close, it's just cross-cutting fractures everywhere. It's just everywhere it's cracked. Now on the bottom side, you see Enceladus, which is an internal diagram, a cutaway diagram. On the inside, you can see, if you look closely, there's something jutting out of the South Pole. Voyager hinted that this was also a young surface, but it didn't get close enough, and it didn't have the right filters, and it didn't have the right viewing geometry to tell us what was actually happening, and hinted that something was different about Enceladus. Most of the other satellites of Saturn, for example, are just densely covered in craters. But Enceladus is much younger, and it's got these strange patterns. When we went back with Cassini, we actually observed venting out of the South Pole. There was active volcanoes also in Enceladus. We needed to go back. Voyager hinted at something was different. But the Cassini mission told us what was actually going on. Triton, which you saw in the movie where we flew past just a few minutes ago, the red marking is an actual erupting volcano on Triton as well. We haven't been back to the Neptune system, but we suspect that Triton is geologically active, a very young surface, even younger than Europa. So it could have an ocean on it. So Voyager strongly hinted that something different was happening in the outer solar system. And when we returned with Galileo and Cassini, we confirmed that. The finding is that ocean worlds are probably a very common occurrence. We used to think of Earth as being the ocean world, the only one that had any water on it, in a liquid sense. But all these examples, and there are others, Callisto, for example, probably has an ocean deep inside. Titan probably has one as well, deep, but probably has one. So there's like half a dozen worlds and possibly some other ones that may have had them in the past, frozen now, that says oceans are very common. And that's important because on Earth, water and life are associated with each other. We need water to live. Water is probably where some of the life that we have developed, although there are certain differences of opinion on where it actually originated. So we want to look at those oceans, and the diagram shows two possible interpretations of what's going on underneath the surface of Europa. One is that the ice shell is thin, the other is that the ice shell is pretty thick, and that there's all sorts of activity that could actually be eruptions of volcanoes on the seafloor, like we have on Earth. On Earth we have the seafloor volcanoes, but we also have what they call black smokers, which is basically hydrothermal hot water that's actually penetrated through the crust and is moved by the heat of the volcanoes and comes up black because it's exsolving materials from the crust itself and bringing those out into the ocean water. So that you can have potentially complicated geochemical and geophysical systems underneath these oceans, but there's no way for us to know that because we can't explore them yet. Not in that sense. We would need a submarine, and getting through an ice shell that's 10 kilometers thick is a bit of a challenge, if you can imagine that. But there are indirect ways we can do that with orbiters that go in and measure the gravitational field and look for signatures of volcanism, that sort of thing. We actually don't know the chemistry of the oceans because we've never sampled it. On Enceladus, those vents, those jets coming out of the South Pole are actually composed of water and salt. And the reason we know that is because Cassini, because it could go back to Enceladus repeatedly, was actually able to go right through the plumes, right through the jets, about 50 kilometers above the surface, and sample them with their neutron mass spectrometer, if anybody knows what that is. I could actually measure the materials that we would need to go back to Europa to do that again, if there were any there. So, one last question you might ask is, why is any of this happening? Ice should be frozen, right? There shouldn't be much happening, right? And the further out from the sun, the less solar heating, things should be colder, and indeed they are colder as you go further out. And this movie illustrates the concept. On Earth we have a tide, and the moon generates it as it goes around its orbit, and also by the sun. The sun does the same sort of thing. On Jupiter, Jupiter is much larger than the Earth, and the result is that the tides on the Jovian moons are much higher and much stronger than they are on Earth. For example, on Europa, if you were standing on the surface of Europa, the surface would go up and down with each tide, which is about a 3-day period on Europa, 30 feet. And I'm talking the actual solid surface would actually lift up and down in response to the gravitational tide of Jupiter. The reason for that is because the orbit of Europa is not circular, it's elliptical. So it gets closer and further away every 3.14 days, or whatever it is, 3.5 days, I believe. That raises a 30-meter, I said feet, it should be 30-meter tide every single day. That amount of flexing introduces a lot of heat into the shell, the icy shell of Europa. It's enough to keep it liquid. It actually melts it. On Io, it's a silicate body made of basalts, dominantly, and some other materials, and that tide is enough to melt the rock itself. That's because Io is much closer in. So, NASA has set, as a result of the Voyager findings and the Galileo and Cassini findings, that ocean worlds are an exploration priority. And we want to go back there. And in fact, we are planning a mission, as you see on the right-hand slide, to return to Europa. Launch date is currently set around 2023, depending on the availability of the launch vehicle. It'll take roughly 6 years to get there. So late in the next decade, we'll have an orbiting mission around Jupiter that will pass by Europa many times and globally map the surface and do radar sounding and gravitational measurements and infrared measurements and a whole bunch of things, trying to determine what the chemistry of the surface is and what's going on in terms of the ocean. One of the things we actually hope to determine is whether Europa is actively erupting any material from the ocean today. Neither Voyager or Galileo were able to determine that. So that's one of the things we want to determine. Now, that's basically the end of the talk, except I don't know if we have 5 minutes. Okay. So, since this is the 40th anniversary, we can talk a little bit about the feelings and perspectives of the team that was launching Voyager at the time of the mission development. And they knew that they were not the first man-made objects to leave the solar system. The pioneers were to do that. So they were going to try to do something different. So they wanted to send a message from the people of Earth to whoever might, Klingons or whatever, might encounter the spacecraft 20, 20,000 years, 50,000 years, or whatever. Or people from Earth who might want to look at the time capsule, although we actually have copies of it, so it doesn't make any sense. But anyway, so they put together a record. And this is the record and its covering, which is made of gold, which gold is supposed to be a stable metal, so it wouldn't decay in space from radiation, that sort of stuff. And they recorded the sounds of Earth. In fact, I was part of a concert about 4 weeks ago from a local chamber orchestra who decided to actually play some of this music as part of their show. One of the unexpected surprises of the Voyager mission was that when we sent sounds of the people of Earth to space, we got something else back. We got, in fact, the sounds of the planets. Now, you might scratch your head and say, you can't hear sound in outer space. Of course, that doesn't make any sense. So matter is needed to do that. You know, sound is transmitted in water and in air. But space is actually, well, I shouldn't say it's full, but it does have plasma, which is an extremely tenuous, thin, unbreathable, because it's simply so low in density, envelope of particles outflowing from the sun and surrounding the planets trapped in the radiation belts. So, I think I skipped ahead of this slide. Oh, yeah, I did. So, that's a teaser, by the way. So this plasma is constantly in motion, responding to the solar wind. So it moves in and out, and it's denser in some areas, and it flows, and it bounces around, and moves around. It's all being pushed around, creating waves in the plasma. Again, this is so low in density, you can move your hand through it, and you wouldn't know it, let alone not breathe. These waves are measured by instruments on Voyager and subsequent spacecraft. And this is a diagram showing the measurements that are made, and you can see there are variations in them. And they all have different signatures associated with different phenomena. Either lightning strikes on the planet can be recorded, or other factors, the shock when the solar wind hits the radiation field, for example. These can all be transcribed into audio frequencies, and that's what you heard in the next slide. Is the attempt to do that, and I'll let this play for a few moments because you'll see that actually will ramp up, and you'll hit basically the outer boundary of the Jovian magnetic field. The movie on the left is actually Uranus. I mentioned that earlier. It should change in a minute now. Yeah, okay, you're hitting this point right there. So you're actually hearing the penetration of the Jovian magnetic field, which is much more powerful than Earth's. Probably the most amusing one, and this is the last one, is that you can actually hear the Saturnian rings. And the way you can hear them is that most of the rings, especially in the outer areas where Voyager went, Voyager didn't go through the rings. That would have killed the spacecraft and destroyed it. It went as far away as it could and still do science. Yet there was still dust. It's a very dusty plane. When the micron-sized particles, which are smaller than the dust particles that we clean up in our own home, strike the spacecraft, they basically are destroyed in a burst of plasma, of ionized gas, around the site of the impact, and the instruments pick that up. And there are thousands of these impacts. I don't have any control over the volume. Sorry. They sound like rain because they're happening so fast. Thousands of small dust-sized particles. It sounds like rain on a tin roof. Which is very different from the sounds we heard just a few minutes ago. Okay. I'm going to skip over that one and say thank you. And we have time for a few questions, but I'm going to stick around for at least 15 minutes to answer any questions that you may have.
And we don't have the usual handheld mic, so if you wouldn't mind speaking up, and Paul, if you don't mind repeating the question for everyone, that'd be great.
How do you know when you got to the end of the solar system and you started, when you detected the edge? Were you just prior to that inside the magnetic field of the sun? Is that the last detection? Did it change the orientation of your magnetic detectors when you left that point?
Yes. We have a very good characterization of the solar wind, which is the particles just bursting out of the sun in the radial directions. So we know that signature very well. And there's a number of indicators, and I know nothing about plasma or magnetic fields or anything. I'm a geologist. I know rocks. That's all I know. So there's directional indicators associated with that outflow and intensity indicators. And when it slows, basically it's slowed to a halt almost at the edge of the solar bubble, which is roughly about 120 astronomical units, something like that, which is astronomical unit is the Earth's orbital distance. So it's quite a distance out. All those indicators were changing, flipping around, and the intensity changed, the directions changed, everything changed. So they knew something was happening, and then it transitions into another. The transition zone is not instantaneous. It doesn't happen like this. It's like several 100,000 miles wide zone where the particles from the sun are sort of braked to a halt, and then you get these other currents and other things which I don't understand or anything like that. And then you transition into the streaming plasma environment of galactic space, whatever that is. Who knows? So that's the best answer I can get on that one. But yeah, there's all the instrumental indicators changed.
There was a different composition in the particles.
Yes, that as well. Oh definitely the helium and hydrogen coming out of the sun.
Some people still argue that we haven't quite left yet, though, right?
Oh yeah, I mean these guys are the people who know something about that.
No, there's people still arguing that we haven't left the solar because it's a
tough
thing.
We're in the transition zone for sure, because things have definitely changed.
I'm wondering if the bottom of the ocean, because the heat flux escaping Europa, how warm it is down there.
Right. We don't know.
Is it hot enough to have black smokers? Because we have a whole independent light system on the bottom of the ocean because there's such an energy there.
Yeah, the question is relates to whether we know what's going on in the ocean floor of Europa and whether there's enough heat there, and we don't know. There's a lot of speculation. Scientists like to speculate sometimes. There's enough heat to, of course, keep the liquid, the water liquid. Whether there's enough to trigger like active volcanoes like Iceland or something like that on the floor is problematic. But there's probably a good chance that there's enough to circulate water through cracks or fissures in the ocean floor of Europa that would circulate water in where it would be warmer and then move the chemistry around, circulate the chemistry. And that's what you want, really. You don't have to have, erupting volcanoes like Surtsey or something like that, but you need some circulation to create some interesting chemistry. And, since we've only seen the surface, we can speculate and try to do some geophysical observations with the next mission.
If we were to build another Voyager today or in the next decade, how would that spacecraft be different from the Voyager 4 years ago?
Well, we have an example of just that. Voyager was designed in the mid-1970s, so it doesn't use CCDs, it uses Vidicon cameras, which are equivalent to the old tube-style television cameras. We launched New Horizons to Pluto in 2006, and that was designed in 2004 or 2003 time period. And it was smaller, the budget was less, the antenna was smaller, and we can only put 4 instruments as opposed to 11 instruments on board. The television camera was much more powerful. We knew this is where the experience of Voyager plays into what happens next, is that we found that these ices are very colorful. And so we had a much more powerful multispectral camera, and we had a very powerful infrared mapping spectrometer, which is a fancy name for an imager that looks at the far mid-infrared wavelengths. And there, I kind of wish I had a picture of Pluto in this presentation now. As a result, we've been able to map the distributions of exactly where the nitrogen ices are, where the methane ices are, where the carbon dioxide ices are, and where the water ice is on Pluto. And that's important for us to see how the geology developed and why it's there and why it's not in other locations. What's the geologic history of Pluto? So that's the partial answer, is that it's the instrumentation. It's the science instrumentation. We knew that you had to go into the infrared. We didn't know that with Voyager, but now it's key. We have to do that because that's where these ices are spectrally done. There are other factors. Pluto has an atmosphere, so we wanted to take an ultraviolet spectrometer along to see what the atmospheric composition was. Voyager had that too, because it used it on the planets. Here we used it on Pluto. So we didn't take a magnetometer on board because we were somewhat limited in various factors, mass, money, a whole bunch of things. And we really didn't get close enough to get a good magnetic field signature. But you can't do everything on the first mission. Anyway. So and there's more to that question than I could tell you, but those are the key things that come to my mind.
Down here and then back.
Amazing. Yeah, after just thinking for a second about the 40,000 years for this man-made spacecraft to get to a star, I first thought it was 40,000 years. That's not very long.
Not really.
And then, of course, in my head, I can't really
long for us.
Really do the math fast enough on comparing light years with the speed of the spacecraft. But I mean, if you're getting to a star, then 40,000 years, that's something pretty special. I mean, the business of the record on there,
Yeah.
I want to point out, Chuck Berry is on that record.
Yeah, and he actually.
And I did hear that somebody at JPL got a report back to send more Berry.
Yeah, Chuck Berry actually performed at JPL the day after the encounter in the mall. JPL has a grass mall, and he performed there for us, and I think he's saying Voyager be good or something like that. But the velocity, the outward velocity of the two Voyagers is on the roughly order of 15 kilometers per second. And it will not pass within those star systems. It will pass a few light years from them. That's why they're on the list. That's the closest pass we had. So anybody who's looking for them would have to be looking for an object that would basically fit from here to the first rows, out 2 or 3 light years, which is a long way away. For us, it's a long way away. A couple of trillion miles or something like that. And it would have to be looking for it. So, yeah, chances of it being found are remote.
So this is where, so if you think about that 40,000 miles an hour, right, so that's a pretty fast speed, right? Even a Tesla can do that, right?
Yeah, well that's...
It's been traveling for 40 years and only recently got outside of our little part of the galaxy. So this is just, this whole scale is just amazing.
Well, that's like from here, that's here to the airport in 1 second.
Right.
Something like that. Which would be nice.
Very fast. The speed of the instrument is constant, obviously, after it leaves the solar system. But it was not constant when it was zipping around, or it changed the speed, right?
Yes. And every time it passed the planet, it got a boost in speed. It actually is slowly decaying because of the gravitational influence of the sun, but it's minuscule decrease in velocity. It reminds me of a story. Voyager got a boost. I don't remember what the boost was in velocity. It was substantial in terms of its approach versus its departure velocity when it encountered Jupiter and then from Saturn. But Jupiter actually decreased in its velocity, so that in roughly 1 million years, it will be about a centimeter short of where it would have been if Voyager hadn't passed by it. So we're doing a lot of damage out there. I mean, yeah, that's true. That is actually true.
Environmental impact.
There has to be a momentum exchange. So Jupiter actually lost, trivial. It's a trivial amount.
Conservation of energy.
Yeah. I forgot that story.
Can you tell us more about the elemental composition of some of these Galilean and more distant icy planets? Does distribution of heavier salts or metals indicate any upwelling from rocky or more?
I'm not sure how I could repeat that question for the monitor, but basically, I think the question is, can we tell anything?
Does the composition of the salts, particularly if they're heavier salts compared to like sodium chloride or something, tell you anything about whether the interior has a solid core or not?
In the fractures, for example, the fractures in Europa, which you mentioned are darker and have some higher molecular weight organic compounds, do you see any heavier metallics or semiconductors or fissionable isotopes in trace amounts?
In terms of the dark markings on Europa and their composition and whether they're telling us something about the interior, they're telling us something, but there's a bit of a debate right now. The Galileo detectors gave us sort of ambiguous results. They could be sulfates, which would have a reddish color. They could be salts, which are slightly different in composition. Those chemistries are more related probably to the ice-ocean interface. And the ice-ocean combination on Europa is about 100 kilometers thick. And then the rest of it's rocky silicates, hydrated silicates, maybe an iron core. The only way to get at that information, what's in the interior, is to look at the gravity signature, as Galileo or the new Europa mission will tell us. And there, it clearly indicates that it's got an icy, watery outer layer and then the denser silicates on the inside, but it doesn't tell us what that composition is. The chemical interaction is probably only in the water interface, unless there's something going on at the ocean bottom, but there we're, again, entering into speculation. There's no way to know whether they're related or not. They could be.
Stephen Hawking recently came up with this rather widespread pronouncement that humans have about 100 years to find another planet to live on.
Yeah.
And I'm curious to what extent that idea is having an impact in the planet science community and anybody's coming up with plausible timelines.
So the question is basically Stephen Hawking's saying we only have 100 years to get off the planet before we're immolated, I guess, is the inference, I guess. I would suggest, based on current events, that we may have no more than a year. But there's always been this drive to go and colonize Mars. It's an old dream. Mars is probably the only place that's practical, I guess. You could do it on the moon, but it's airless, and giant colonies with greenhouses and all that sort of stuff. Maybe, but in terms of a drive to go, that's a political question, I think. The people are always pushing, let's go to Mars, yeah, and that's great. And maybe, but whether it'll sustain an entire race, I don't know. That's not something I really think about very much myself.
So there's an interesting calculation that a colleague of mine gave to me, which kind of puts this in perspective. The Earth has 7 billion people on it. It's growing at 1% a year, so there's 70 million new people on the planet Earth every year. If you want to keep the Earth where it is now, you have to take those 70 million people and send them somewhere. To somewhere that doesn't want them, because Earth is the only place that can really sustain it. That's not very feasible, so at the very least. But Jeff Bezos, who you've probably all heard of, right? Especially if you did Cyber Monday. With Blue Origin, one of his big goals about why he's investing his own money into space, leaving the Earth and building rockets, is not so much to take people off the Earth, but it's to take all the stuff that is affecting the Earth, the heavy industry, the mine, all the stuff. We still need that energy, we need those resources. Take that off planet, and then the Earth becomes the place that sustains life without us messing with it. And so that's a kind of interesting idea, and there's a lot of discussions going around on that, but that's not a planetary science talk, that's more of a commercial space talk. So there's a lot of interesting things happening, and we may be driven there just because of the inability of the Earth to sustain us. And as we learn more, I think, if you don't mind me sort of putting words in the Voyager mouth, is as we learn about how precious life is, even if there is liquid water and organic material on these other planets, there's nothing quite like us as far as we know. At least we won't know for 40,000 years, right? We learn a lot from space to try and fit into some of these other arguments. That's my soapbox.
Well, we can also look at what Voyager and the entire NASA and Russian and other planetary exploration programs have revealed about the solar system. And I'm reminded of a chapter title in an old book I read when I was a kid, No Hiding Place. There's no real place for us to go. Mars could be sustainable, but it would require developing its own infrastructure and to build structures that protect people because you can't breathe the atmosphere. There's an atmosphere. I mean, I love The Martian. I thought that was a great movie, but that was not a sustainable environment. That was a temporary exploration thing. So yeah.
Remember O'Neill colonies? What do you think of those?
Actually, I'm not familiar with those.
O'Neill colonies, yeah.
Colonies in space.
This is where I get to advertise the TV series The Expanse. Yeah, I met one of the actors last weekend.
I like the thing in Interstellar, maybe. Anyway, yeah. Any other?
Yeah. So we have let's work. Someone had one back here, and then we'll work our way down the front here. Sir.
You talked about tidal heating. That energy got to come from someplace, and does that have any measurable effect on the orbit of the planet? Because I assume the energy is coming from the orbit.
Yes. Yes.
That we're going to be able to detect over our reasonable future.
The question relates to tidal heating and what its origins are, orbital decay. The orbits of the satellites evolve with time. They interact with each other. They're large objects, so they sort of sense each other. And Io, Europa, and Ganymede are actually in a resonance. Their orbits are multiples of each other. 1, 2, and 4. So they actually are in the same position each time the outer planet goes around. They're all on one side. So they're pulling each other out of round. The orbits are not circular. So that's the mechanical reason why there's tides, is that the gravitational interactions of the 4 satellites are pulling their orbits out of round. If the orbit's out of round, that means it gets closer by a significant fraction during part of its orbit. That means it gets closer, and each time it gets closer, it gets distorted by the gravitational field. Jupiter's like, 1,300 Earth masses or something, some large number like that. I can't remember the exact numbers. I never remember these things, but it's huge. So when it gets closer, it's going to distort, and that's where the 30-meter figure comes from. That's the distortion. It's because the orbit is forced to be out of round and moves the satellite in closer during part of its orbit, and that generates a lot of frictional heating. The rock basically is doing this sort of thing all over the place. So that's what causes the heat. Now, I'm not sure that answers the question, though.
Every time that planet heats up, it's taking energy from someplace.
Right.
And the only source of the energy that I can see, unless I'm missing something, is the satellite going around Jupiter, which to me says that the satellites can get closer and closer to Jupiter. That makes sense?
I'm trying to remember. I knew this at one point.
There's an orbital
moving
energy associated with the system, and some of that energy gets modified by this.
I think they're moving out.
Potential energy changes.
I think they're moving outward, but I might be wrong. My memory is not good on this particular point. I think they're moving out.
There is a modification of the orbit.
Right, yeah, it is.
As you pointed out,
The orbits are changing in dimensions, but the fact that they're in orbital resonance means that they're actually kind of locked in to some degree as well. They can't move very much at the present time. Jupiter is actually losing some energy as a result of this interaction as well. It's distorting Jupiter itself.
So why
Very
does it
minuscule.
give off more radiation than receives from the sun?
I don't think it's...
Yeah, Jupiter's contracting.
That's a different problem.
Millimeters a century, and that generates internal heat.
Yeah.
It's twice as much.
Yeah, that effect is minuscule compared to the collapsing shell of Jupiter itself.
So we had 1, 2, and 3. So
I think over there in the white shirt, maybe.
Okay. Blue shirt, and then we'll come back to that. Yeah, no, this right here first.
Okay, and then we'll probably wrap it up.
Yeah.
How do the results from New Horizons change our appreciation and understanding of flight?
Oh.
We have almost 2 days.
That's a long question or long answer. How does New Horizons results of Pluto affect our interpretation of Triton? And I didn't talk about this actually, so I'm going to try to give you the shortest answer possible, and we can follow up on it later if you want. But Triton is indeed a satellite of Neptune. It's in a very actually in a very circular but tilted retrograde orbit. It's going backwards compared to what the other moons do in the rest of the solar system. But it's almost exactly the same size, almost exactly the same density, and almost the exact same surface composition as Pluto. But it got captured, we believe, by Neptune some time ago, and in the circularization of the orbit, it basically got melted from the inside out. Pluto never experienced that. The surfaces of, and we were very interested in this idea on our approach to Pluto, was whether the two bodies would look alike or have shared characteristics. And again, the 30-second answer is that mostly Pluto doesn't look very much like Triton. Triton has been completely resurfaced. There's no old terrains left on it. But Pluto is much more complicated. There's a lot of old terrains, ancient terrains, let's say, and a couple of very young terrains that are basically frozen nitrogen ice sheets, composed of a couple kilometers of frozen nitrogen, just a layer of it on the surface. Triton doesn't have that. So probably the reasons for those differences are that Triton would probably look like Pluto if it hadn't gone through this catastrophic capture sequence at Neptune, which melted the whole thing, basically. It just melted the entire body, at least the outer half of it, anyway. So that's the short answer.
Last question.
So could the plasma music or anything else that matter from like Voyager or New Horizons be used for evidence for like a ninth planet?
For what?
A ninth planet.
Some people say Pluto's a ninth planet. The plasma waves, I don't know how that would... the plasma waves are all related to the magnetic field and the radiation belts, primarily, that are trapped around the planets, much like our Van Allen belts around the Earth. If you did a similar mission through the Earth system with the same type of instruments, you could get the same type of plasma audio or plasma wave signatures, which you can then translate to audio, of course. But Jupiter is much larger. Saturn has one, Uranus, Neptune. They all have these magnetic field signatures, or magnetic fields, which trap the radiation belts. And that's the primary thing that they're measuring. And then you get it with the solar wind as well. A solar eruption, a solar coronary event would create a disturbance in that, and you would get a similar wave pattern. But they're all localized to that planetary system. We're not really feeling anything that's way out in the outer solar, at the edge of the solar system. So that would not be the way to do it. Gravity waves, that's a different sort of thing. That might have something. You would detect a disturbance in the orbits of that planet. And nobody's really picked up anything that's measurable.
I mean, it'd have to be big enough to have a magnetic field. The magnetic field would have to be strong enough to have an interaction so it produce the waves. Because if it's anything, it's twice as far away, I think, as Neptune. So that's a factor of 4. It's R squared and so. But that's how one of the things we're trying to do is use that approach to see if we can determine if these exoplanet systems that are now being discovered have a magnetic field, so that if the planet is an Earth-like planet close to a sun-like star, if it doesn't have a magnetic field, the surface isn't going to be very habitable for complex systems like us. And so one of the things we can do is predict what we might expect a signature to be with that interaction, and could we see that in the radio and sonar? We're working with folks on that. I think maybe just one last question, if it's a brief one. Going back, please.
I know it's brief, but I'll try to make it. So you talked about orbiting spacecraft going to Europa in the late 2020s. But what would be a projected timeline for an actual ground probe, and how do people make that decision? How do scientists decide, okay, we're going to send a probe that's going to actually go to the surface?
Okay, so the question is, how do we decide, or how do we get a probe onto the surface of Europa, basically? And there are discussions about that going on right now. Europa, to address the challenges that are inherent in going to the surface of Europa, it's about the size of the moon, so we can think of that, but it has no atmosphere. You can't use a parachute like you do on Mars, to land on Mars, or Titan for that matter. It's also bathed in the strongest radiation belts that are in the solar system. So it's a very hostile place. You have to harden the electronics to survive for a period of time. And it's also within the Jovian gravitational field, so even getting to Europa itself requires a large fuel tank to break into orbit, because there's no way to use a parachute, as I said. That makes it expensive. And expense drives what we can do, often in the case. But there is an impetus to go there, because there is this exotic, uncertain chemistry on the surface. There's the possibility of something from the ocean getting to the surface and being something we could sample. So we would want to go there and actually see, okay, what is the ocean made of, if we can find a place where the ocean's erupting. Which is why we have to go back and to do the mapping first, to determine as best we can what's on the surface, how did it get there, is there any indication of the exotic chemistry, and then go there if we can. That would be the logical next step. And so there's a lot of trading, horse trading going on in terms of, well, what kind of instruments should we put on this lander, and how do we get it to the surface and make it affordable, and because you can't do everything. The more instruments you have, the heavier it is, and the more expensive it is, that sort of thing. So you got to sort of figure out what is the key question, and how are you going to address it with the minimum amount of mass, and it's just but there are extensive discussions going on right now to see whether it's feasible. I mean, our local congressman is behind most of that, actually.
So the idea is that the orbiting mission is going to give you more information to tell you whether or not we should go to the surface. That's sort of
I think it's probably safe to conclude that everybody in our profession, and a lot of people on the outside, think that we should go to the surface. So that's not a difficult question. The question is, can it be put into a package that will not cause congressmen to choke? That gets you into other areas where I don't want to go right now. But yeah, they have to say, yes, it's worth doing, and we can afford this and justify it to the people, because it is the people's project.
Thank you for all the questions.